Hey everyone. So yeah, I'll myself start the talk for the today. So basically, I've been working in machine learning for about 5 years now. Published a couple of papers in the space. Worked as a research scholar in UC Berkeley and MPI Frankfurt, and most recently, I've been leading the Federated Learning team at OpenMind. And following that, I've been running my own venture called Nimbalech. This talk is more about how machine learning has been done previously and how I feel that the next era of machine learning would be based on. Basically, how should we actually work towards ecosystem to build out tools, to build out algorithms that can overcome the challenges that has been proposed by the current AI, the AI systems that have been deployed on the cloud, and primarily relying on data collection from all the different sources. Right? Federated learning is one such technique. It was introduced by Google in 2016, and since then it has been gaining a lot of traction in the research community. Uh, Google was one of the first companies to actually deploy it as well. And after that, you could actually find FL being deployed in lots of different use cases across healthcare, across fintech, across uh, all the privacy preserving solutions, right? And with the recent bump in GDPR and CCPA, it has gained a lot more traction in the ecosystem as well. So I'll tell you about what it is and how we can actually go about in deploying such a solution. So one of the biggest tenets of federated learning is that it decouples data collection and model training. So I know every time we consider AI, every time we consider machine learning, we treat it as synonymous to data collection. You cannot train your machine learning models without any data, right? But how do we actually protect, how can we actually train those models without hampering the privacy of the users? How can we actually train those models without copying those data, putting it on the cloud? And with more and more data being generated every day, it's actually a bigger problem to keep all that data in the cloud. I think this, since we all of us are from MLOps and different spaces, we know what kind of challenge it is to copy all the data, put it on the cloud, maintain the data security, and all the challenges that comes along with it. Right. So I think usually in these reading sessions we already have shared the papers with each other. So one of the papers that was shared along was the introduction papers of federated learning. It was by Brendan McMahon, and it introduced the concept to the world on how can actually this be done. Right. So let me give you an overview of what federated learning is actually by the definition and what it means in production, right? So federated learning is basically doing machine learning across multiple entities. So these entities could be smartphones, these entities could be servers, these entities could be even all these IoT devices. We don't care. The point is that all these entities will together train the model that you need to run the inferences. So the training paradigm itself has been distributed across all the devices, right? This, the definition that you are seeing over here is from Khare et al. It is advances and problems in federated learning. It was a workshop paper that's a good survey that compressed all the information that have been built and generated over the last 5 years. Do check it out over the time. Yep. So, right. So let's see how does a federated learning cycle usually works. Okay. So in the previous diagram, if you see, there's a cloud entity which has some kind of model, which is being passed to the servers, which is then passing it to the devices, and each of these devices are training these models locally and sending the updated models back to the cloud, right? So how a usual FL cycle will work is there would be some entity that hosts the models, the original machine learning models that you want to be trained or to be fine-tuned. Now, all the distributed entities, all the clients per se, they'll download the models from the cloud or from that central entity, train it locally on their own data set, which most of the time is non-IID. So you cannot expect two users to have similar kind of data distribution, right? So similarly, you cannot have, if you are doing it in a server-based federated learning, then those servers will have those data sets. So each server could represent one hospital per se. So in that case, the data is always non-IID, and you have to mitigate each device trains the model locally and then updates all the models back to the cloud. The cloud, there's different kinds of algorithms for aggregation. Some use error feedback, some use different kinds of second order gradients to merge that information that is coming from all these different devices to build the final updated model that you can again use for the entire FL cycle, right? So if you look into how a training of a federated learning model works, you start with the client selection. That is, in case of, say, you are training your recommendation engines, right? So in that case, you have millions of devices, each possibly can train its own model for the user. So how do you run the entire FL cycle? How do you train your models, right? So you cannot actually ask all these devices to train the model and average them together just in a single step or in these steps. Because the same paper that we shared earlier, it showed each model that participates in the cycle is associated to a certain data set, is associated to a certain batch size. So if you increase the number of clients way too much by, say, 20,000, 40,000, or even 100,000, then what happens in this case is your overall batch size tends to reach infinity. And in general, just like it happens in SGD or stochastic gradient descent, you cannot have too high of a batch size because that removes the entire stochasticity that was there, that provides smoothness to your loss functions. Right. So what usually happens in production is, say, I have 160 million users on which are collecting, which have their own data set on their devices, and I want to train my recommendation engine using that data that is available on those devices, right? So I'll filter out of these 160 million devices, some 20,000 devices, based on how frequently can these devices participate, how much time do they take to actually compute the entire model update, run the local training steps, what is their network bandwidth, and all those different kinds of factors, right? And once these 20,000 devices are selected, they download the model from the cloud for training. So these are the actual model weights that needs to be downloaded. The third step is training them on the device. So you can use Adam, you can use SGD, you can use any kind of training pipeline. In fact, whatever you were using on the cloud, you can actually use it on the device itself. There are libraries that enable you to move from these cloud-based pipelines to the edge-based training pipelines. Once you have trained it, say you have run your 100 local iterations on the device, then you do what we call as reporting. So these are the updated model weights that are sent back to the cloud. So usually, if your models are big enough, say 1 GB or 2 GB, you cannot expect the users to empty their entire data quota for updating your models, right? So we don't send the exact models in this case. What we do send is the difference in the gradients, so the delta that is there. And often the times you even don't send the delta. You compress those gradients further by, say, just picking up the top heavy hitters from those gradients, right? So say top 10 gradient coordinates out of those things, or top 1 million gradient coordinates. So that there are, again, multiple papers that have been published in the space that are all focusing on how can we actually reduce the communication of data that is happening between the server and the device, right? So training on the device is cheap, aggregation on the cloud is cheap. What is costly is the data movement that happens, the movement of the models that is being done across the two devices, across the cloud. So what we do is we apply different kinds of compression schemes, different kinds of lossy mechanisms to find out the top gradients that can just help us learn the entire model. and once gets segregated from a lot of different sources. So yeah, once the reporting is done, all these models are sent back, used together by the cloud aggregation service, which can aggregate them together to form the final global model. And that global model again participates in the secondary cycles of client selection, model download, and local training, and all those things. The thing to note over here is the aggregation cycle or the aggregation step by itself can be very complicated. So the federated averaging paper simply just averages those models out, or a weighted average of those models. But there are schemes to do error feedback, to do basically mitigate the losses that have been done while these communication has happened between the devices. Right? So that's an overview of the FL cycle. And as I was mentioning, the federated learning itself as a concept just means that your training data is distributed across multiple clients. So if you want to do machine learning, but your data is distributed, right? So that data can actually be distributed in two different paradigms. One is, say, when the data is distributed across servers. So it could be cross-silo FL, where each server has the entire data point, but the intersection of users that are there on one server and the other server, they are different. So for example, you have 1,000 users, 500 users, the data of 500 users is available in server one, and the data of next 500 users are available on server two. So how do you train this model? Distributed silos. So that is cross-silo FL. Now, vertical FL is more about when the same data point is distributed across multiple servers. So you had 1,000 users, you have the data for all the 1,000 users on one server, but it's half the original data point. So say the data point or the features that you feed into the neural network are 1,000 dimensional. 500 dimensions are available on server one, while the another 500 dimensions are available on server two. So the same data point of the user is distributed across two different servers. Usually vertical FL is much more important in decentralized identity, where say you have access to Twitter's dataset, or you have access to Google's dataset or Microsoft dataset, but you cannot actually merge those two datasets together. Otherwise, you would be getting stuck in a huge GDPR and CCPA fines for user identification across data. Right? In the third part, in a server-based FL is decentralized FL. So usually when we are talking about, there is an aggregating entity, right, who's aggregating the models that are coming from different sources. So in the most naive deployment of federated learning, what happens is you host a server, that server is your aggregator. And all your devices who are training, all the trainers are updating their models and sending back to this central aggregator. In decentralized FL, there is no central orchestrating agent. No one can command anyone to start an FL cycle. So for an example, an ideal case of this would be along the lines of autonomous cars. Right? So each car has its own aggregator and its own trainer, and it would be getting the models from whoever is beside the car. Right? So for example, my car has 4 other cars beside it. Each of them are training their own models locally. This car just asks all its neighbors to give whatever models they have trained so that it can learn from their data set as well. Right? So think of it as a gossip protocol, each one gossiping its model to other one, and the FL cycle is keep on happening. Everyone is a trainer, everyone is an aggregator. That is what we call decentralized FL. The second part is more on edge-based FL. So edge, as in there are different kinds of edge, but what we are talking about over here is the devices that are in the hands of the users, or the devices that are basically at the very edge of the internet, right? So your smartphone, laptop, Fitbit, IoT sensors, and all those things. So usually in this, there's a term called cross-device federated learning, which is exactly like cross-silo, but instead of servers, you have devices. So what the thing that changes between the two is cross-silo has huge network bandwidth available. The servers connectivity is reliable. The servers do not break in between. The end clients themselves are much more secure in terms of doing the computation. They are much more trustworthy. In cross-device, you basically lose all those assumptions. Half the time, the device won't be connected to the network. Even if it's connected, it would be on a poor internet connection so that it cannot actually communicate well with other devices. Then the device's compute capacity is also a huge, you will find a huge diversity of these devices, right? So there would be a $50 smartphone and there would be a $2,500 smartphone. Both of them doing their training pipelines. While one takes 2 days to finish the same training pipeline, other takes about 1 hour to finish the same thing. Right? So there's huge difference in terms of the compute power, the RAM that is available, the network, those things. So edge-based FL on cross-device has to deal with all these things. Then decentralized FL is similar to the server-based decentralized FL. It's just the devices itself will be having a P2P connection directly between them and orchestrating their own federated learning cycles. So again, working in a opportunistic network / distributed graph kind of function. Yeah. So I was talking about why do we actually need to think about federated learning? Why my current machine learning pipelines are not good enough? Why should I even switch to FL? Right. So for example, I'm running my recommendation engine on 160 million users. I don't have any problem with that. Why should I try to do these things? Why should I go with federated learning? So one of the things is since the entire focus of ML at this point is to bring personalization, federated learning enables you to reach hyper-personalization, right? So you don't, since the entire model is not being hosted on the cloud anymore, it's being trained and run on the devices, you can have 1 billion different models for 1 billion different users, right? So every device has its own model that specifically caters to that particular user. So there are multiple algorithms that have been presented in this space along the directions of meta learning. So where each task is basically a user, and that model focuses on how to perform the best for that particular user. It does not need to care about other users, right? So the same model, the same data, just trained via federated learning, and you get better performance. The second is federated learning is already much more compliant with the privacy regulations across the world. Because if you look at all these compliances, what they say is you cannot have personally identifiable data, right? If you deal with that data, you have to work up all these constraints. You have to ask for the consent, you have to maintain data accountability, you have to ensure that the data gets deleted over the time, right? And complying with everything, it's again still a spectrum. So irrespective of how much you do, you can always be liable. You are always liable for further fines. Now, what happens in this case is, since you are not sharing your raw data with the party anymore, what you are sending out is the model, the extracted information, which usually is not personally identifiable. You can further add differential privacy and SMPC kind of schemes for aggregation to even remove any slight chance that data could be extracted out from that module. Right? So when the model is being sent out instead of the raw data, first of all, the original copy of the data always lies with the user. You do not have that raw data, so you cannot use that data for any other applications. So what happens in this case is, since you got your model, your end goal was to provide them personalization. Your end goal was to learn insights from that data. And when you ask for a consent for a particular application, the user gives it, right? So you have a much more accountable data pipeline for these regulators as compared to anything else, because that model will solely be used for that particular application. The data accountability is way too high in federated learning as compared to any other pipeline. And once you aggregate those models out, right, from the devices, those models are no more a personally identifiable data. They are business data. You don't even fall under the purview of GDPR in those cases. Third part is data security. So this is more along the points of reducing the exposure that the attack surface for your data for your data or for your pipelines. The original data never leaves the user device. Even if something happens on the device, the only part of the pipeline that would be exposed to the hacker or to that person would only be the user's device. Your cloud pipeline is not being affected because of that, right? So that if someone hacks all the others users across the pipelines, yeah. Third part is that federated learning along with inference on the edge is bluntly cheap. The only thing that you're doing on the cloud in this entire thing is aggregation. The most complicated and the most compute intensive thing is being run on the user's devices. So I can say that with certain set of accommodations, you can run a recommendation engine for 100 million users with practically zero cloud cost. That's the difference. So these are some of the points I wanted to mention along how AI has been one of the biggest expenditure for any enterprise in terms of its cloud cost, right? And we don't even need to pay this. Like AI on the cloud is not the ideal solution for the pipelines that we are building out. Machine learning, recommendation engines, personalization, all these things should happen and they need to be happening for better and better utility, but they don't need to suffer from the same issues that the cloud is facing around data leaks, around all those things, right? But if all these things are so rosy with federated learning, why hasn't it been taken into production yet? So there are a couple of challenges that that you as a developer or MLOps engineer would be facing when you are productionizing these pipelines. So one of the things is handling model biases. So let's say you picked up 20,000 devices who all of them should be submitting their models back to the cloud, right? So usually what happens is out of these 20,000, only 8,000 to 7,000 to 8,000 devices would be able to submit their models to the cloud in the time frame that was given to them. Now, in these 7 to 8,000, there's a larger probability that you'll have phones like iPhone or Galaxy to be much more available during the training process, right? They can train much faster. The users who are owning these devices usually have much more stronger internet connection. So your overall averaged model that you get out of these devices can become biased towards the richer section of the society. Right? So you have to deal with these kinds of model biases while you are doing the device selection and while you are doing the aggregation. It's very critical for your performance across the different devices. The second part is model security. So let's say I removed all the devices I carefully balanced all my model updates that have been coming from the devices. I specifically chose a larger number of weaker devices so that in time I could get decent number of devices to balance out the distribution across the different smartphones, right? But if say out of those 3,000 devices, 500 devices were malicious, and they were all trying to just sabotage my data pipeline, right? What they will do is they'll just submit arbitrary model updates to the cycle. And if they get averaged into the pipeline, your entire model that you get from the cycle gets affected. So you have to ensure how you can remove these kinds of malicious workers from submitting their model pipelines into the submitting their models into the main pipeline. Now, both of these things are something that now it's possible to deal with, and there are coming up lots of tools and technologies that enable you to do threat modeling for malicious workers, that enable you to handle the model bias, basically predict what kind of devices, uh, uh, how many fraction of the devices would be able to submit in the time frame, and carefully manage the overall bias of your model. Right? But even then, there are problems like when you're trying to use an FL algorithm or federated learning algorithm to aggregate these pipelines, to run these pipeline, aggregate the information that is coming, you have to test them out. You have to tune their parameters, right? And if you look around in terms of the libraries that are available, there have not been libraries that can enable large-scale simulations for you. So even in the research works that we see, there are often papers publishing and demonstrating their use cases across 40 workers, 100 workers, and in best to best cases, 1,000 workers. Right? But if you are deploying your recommendation engine over 100 million users, you would at least want your pipeline to be simulated with 100,000 workers, right? And in those pipelines, you would want to simulate network delays. You would want to simulate different kinds of device constraints that come into the product. So there were no libraries, good libraries at that point of time. Libraries like Flower and others have been moving along this motion, but still they do not support that kind of scale. And lastly, the field itself is pretty new. As I mentioned, it was started in 2016, right? So there's been a dearth of talent in the space to build out this ecosystem, to build out all the libraries that are necessary for this thing, right? So these have been one of the few challenges that I saw while I was building out all these technologies for everyone when we opened up these production tools so that businesses can deploy FL into their system. And that's how basically Nimble Edge's community started. So we totally have been focusing around building this ecosystem for federated learning along with our other fellow developers, so that we can build this simulator, this federated learning simulator, which can actually enable large-scale testing, large-scale training, and simulations for all your federated learning strategies. There's a research group in the community as well who's bringing up new FL algorithms for recommendation engines for NLP and various other use cases. At the same time, there's also production-grade software being developed so that you as a developer just have a one-click deployment solution for your FL cycle. You have the entire cloud pipeline deployed along with you. It will automatically be serialized. It will automatically be converted into an FL algorithm that can be trained on the device directly. And of course, we are working on privacy schemes as well. So what we feel is that one of the reasons we started out this community was to actually enable all these kinds of different challenges that we as developers are facing in deploying ML on the edge, and as a community bring around all the specific extensions, all the specific projects, all the specific in alignments with the different projects. So how do you deploy it on the cloud? How do you integrate with your existing cloud pipelines? How do you integrate with your applications, Android application, iOS application, and web? So that's an ecosystem that we are building over here. So I think that's the overall view about this thing. I think, Andre, we can take up questions now.
Awesome. Thank you very much, Varun, for your time today. Wait,
yep.
Let me see here. Okay, so folks, does anyone have some questions for Varun? I have a couple. So, okay, I think I can kick this one off. Varun, starting off by you mentioned it a little bit on the beginning of the presentation regarding the training procedure. According to the first paper, the introduction one. So I think there's a really hard problem here regarding the best way to train it. From what I see, on the one end, you can do like the paper says. Basically, you run for each client, you run a total epoch. For example, you can even train on the entire train set of each one of the clients, and then you get a model, and then you send the entire model to the central server, and you average models.
Right.
That's one way to do it. Another way, I think you mentioned it a little bit, is instead of sending models, we can actually send the requests, the gradient as requests. For example, each step of the gradient, and you can even apply compression. Regarding in terms of performance, on the one side, you send a really small number of requests, but really large ones, and also you are training for a larger number of steps. On the other side, you can train for a smaller number of steps, but you will send a lot of requests with the gradients, which are also smaller requests. Which one of these two have you found that leads to, for example, better model performance?
Right. So it will actually depend on the case that we are setting. So for example, if you are looking at cross-silo FL, where this communication is actually much more reliable and cheaper, you will actually focus more to do smaller local computations and larger device computations. But if you are running it on the edge, you have to minimize the communication in any way.
Mm-hmm.
So your priority will always be to actually run more and more computation on the devices and have minimum number of updates. If I tell you about production, most of the time in 2 to 3 months, usually a device participates only once in the entire FL cycle.
Okay.
So you even do not have multiple communications happening with that device.
Okay.
So, but what we can do is say we have 2 million devices, right? So we'll break it up into segments of 20,000. So we'll run first iteration with the first 20,000 devices. Then we'll get our updated model, then send that updated model to next 20,000 devices. We'll then train it and then send it back. So that's how we do multiple iterations of an FL cycle rather than asking the same device to do training again and again.
Yeah.
In fact,
okay.
Yeah, in fact, that is one of the things that we have to ensure that the same device does not participate in FL cycle multiple times. Otherwise, your model will get biased.
Of course. And regarding, you also mentioned it, that one I didn't read on the paper. I'm not sure if they mentioned it. You referred if you send gradients instead, and you mentioned like sending top gradients. How do you actually do that? You just send positions of the gradient vector? How do you actually that work?
One of the papers that I really liked with these things was a paper called FetchSGD. It's from Johns Hopkins University and Google Brain team together. And what they do is they actually do sketching, how we used to do it in streaming data pipelines, right? So for example, if you want to calculate frequencies of different words that are coming in a streaming, in a data stream. So you use count sketch kind of algorithms to approximate the frequencies, right? Similar is the kind of case that they are using to identify the sketch of the gradient. So, and that is so phenomenal. Basically, it brings about the size from the original n to logarithm of n. So you would be communicating log n gradients rather than the original one.
Okay.
The paper's name is FetchSGD.
If you can write that one. Also, David and Shivam asked some questions. David, what are the frameworks for federated learning apart from yours, of course?
Of course. So basically, when we started out this in OpenMind, that was one of the first ecosystems in the world to do FL. Then MLH, of course, took it forward. There are one called TensorFlow Federated that is more focused towards TensorFlow pipelines. Then there's Clara SDK, that is again from NVIDIA, but Clara internally uses our stack only from OpenMind. Then there's one from VChat that is focusing on cross-silo FL. And if you want to do simulations, there are a couple of libraries like Flower and FedML, but they do not support edge execution and edge simulations kind of thing. So you can just run basic ML training pipelines on them.
Shivam also asked a good question on the chat. For the edge case, since the data is distributed, how do you actually get intuition regarding debugging or models, since you can see really the data?
Yeah, that's actually a good question. And what we need to do is actually gather statistics from those devices and sync with the cloud time to time. So you actually make what I call codes in terms of characters. So basically, plus will represent something, minus will represent, say, 401. In multiplication will represent some error in a computation, right? So you basically codify in a particular set of errors that you face, and you keep on logging this every time you run the training pipeline on the edge. You also log the performance of the model on a held out test data that is on the device itself. And all these things are synced over the time so that you can see how your model is being performing and what is the distribution shift, what's the data shift, that is the concept shift that has been happening over the time in production.
When that happens, you just like send the most up-to-date global model for the client, or do you actually like imagine, for example, that a group of clients or some client has been facing a lot of data drift, for example, or concept drift, and that you mentioned triggers it as an alarm. How do you tackle that situation?
Right. So there are a couple of ways for this. Usually, one of the standard ways that we do on the cloud as well is to train the models every 15 days or every once a month, right? At least to deal with the concept drift, to deal with the data drift. What additionally thing that you can do because you are on the edge is you do not need to update it for all the other users. You can just fine tune that model on the dataset that was there on the device. So with the personalized federated learning kind of algorithms, that is also possible because each user, each device would anyway be keeping a different model in that scenario.
Regarding the training, do you use, for example, I see this like, for example, take the one use case of FL that I liked was, for example, the typing one, where for next word prediction or something that the device really trains on our ways of how the vocabulary that you use the most and whatnot. Is there like a way, for example, maybe like in a city, people usually talk the same way, or inside a community, and then to have like a global model just for the community, like in a hierarchical structure? Is there something like that?
In fact, yeah, and that's usually what we call hierarchical FL along those directions. So instead of having one aggregator and all the trainers inside it, what you can do is have, say, 500, 10,000 aggregators and then master aggregator over these aggregators. So you have one global model, you have one smaller model for each of what those aggregators are hosting, right? And prediction is you can do all this when you are doing client selection. So for example, if I want that, okay, I have this particular section of my population, which I want a different model for, right? Say software developers in California. I want a different model for them while I need a different model for software developers in Europe. So while I'm starting my federated learning cycle, right, I'll at that point just filter out all the candidates for the device selection. So I'll only do the device Californians, while I'll only do the device selection for Europeans while that is happening. So while the FL cycle is running, right? So it's the Venn diagram and doing all this intersection is basically the intersection that you have to do in device selection. Everything else becomes automated. So that's the easy part over here.
Interesting, man. You know, a lot of companies that have like products on this, like specifically that tackle this kind of that have really deploy and handle these kind of solutions with FL.
So yeah, so like Gboard has already deployed it. It's running across 1 billion devices already. Siri is already deployed it. Google Assistant has deployed it. Samsung has deployed Federated Learning in its own
Mm-hmm.
solutions. But yeah, it still has to be taken up. The tool stack has to be matured enough so that we as general developers can actually use it directly as well. So yeah. So basically, the technology has been proven at scale, but the adoption needs to make it easier for everyone to adopt production pipeline.
Yep. The advantages you mentioned were really interesting. Not only the data privacy one, but also the cheap it is. Like since you are actually leveraging the client's computational power instead of you paying the cloud resources. Those two are massive.
Yeah,
Yeah.
yeah, and like your users would be happy to do that, right? They don't anyway want to share their data with the third party, but they do want to leverage the benefits that they get from the AI. Right?
Mm-hmm.
That's their perspective, and if you are giving them that and saving your money at the same time, why not do it?
Exactly. There's really some nice way. There's a good vision for this area. Yeah. Okay, folks. Does anyone has more questions for Varun? Well, I still have one, but it's when I read the papers, Varun, I actually sent you a message with this. It's not. Oh, let's see. I'll ask mine on the end. Oh, for security, this can be also bigger danger if, say, you have a pipeline that can run code on lots of edge devices.
That's exactly, and that's why you don't want to run these code bases which are insecure, right? So, for example, I am installing Netflix's app. So, Netflix's app will have its own model that comes itself, and the only code that I would be allowing to run on my app is the Netflix's recommendation engine. I'm not allowing some other third party to send their models to my device and let them run it on my device.
Varun, and like by taking this idea of federated learning, imagine like for example, you have in your company. I mentioned it like for example, guys. Imagine that you are working for a. You want to do like sentiment you want to basically you or translation. Yeah, it's a translation. Imagine that you are working on a translational model, and you have a group of different customers. All right, and all of them need to like make translations. For example, you have different kinds of journals. You have CNN and other kinds of journals, all right? And they want to translate their newspapers into multiple languages. So there's one question which was like, for example, can we really like take this idea from federated learning and basically have a take these companies as clients and take a separate model for each one of them, and then you in their training procedure you actually use this approach of having a global model that really averages across all the clients, all the companies, in order to maybe have better, basically drink from all of those data in separate and then combine it in an aggregation. Varun, do you think
Exactly.
that might
And
work or just fine tune it? Yeah.
yeah, exactly. And that's actually one of the use cases of cross-silo federated learning. So a typical use case has been along healthcare sector. So every hospital has its own data and they do not want to share that data with anyone else. But you as a company who's providing data analytics to those hospitals want to train your models on those data. You even want to personalize your own models with respect to the patients that those hospitals are facing, right? So maybe a particular hospital faces more cancer patients while another hospital faces more of pollution related patients, right? So you would want to adopt your solution suite accordingly for both of those patients, both of those hospitals. So that's where this federated learning works extremely well, because that's what I was talking about, right? Think of it as meta learning tasks. So each hospital or each server in this case, and in your example, each translation server basically is a task that your models have to be learned. And what you are trying to optimize is that ideal initial state from which everyone can start off and retrain their models locally.
Yep.
So yeah, and this is one of the benefits. So we do not have to deal with non-IID concerns in federated learning because by default, everything is non-IID. And so we can allow these models to be personalized and run on those devices. The only thing is, if you are running inference on the global model, it will always be aggregated. And if you want to personalize those things, you'll have to run that on the personalized model that that particular user has, in this case, or that particular server has, right? So your model would be running on their servers in that case.
Exactly. Perfect. Folks, anyone wants to do one more question or a couple of them? Varun, I think we can wrap this one up then. Thank you so much for coming here today. It was an awesome talk.
Awesome. Thanks, Andre. Thanks, everyone. Nice to meet you all. We can all discuss further things in the reading sessions, right? The channel is over there.
Yep.
So if you want, if anyone has any further questions, I think I'll be there to help them out.
How can people reach out to you, Karen?
So we have a Discord channel where there are lots of other professors along with us, other students and developers. They're all working in the same space. So if they want to reach out to me, they can reach out to me on Twitter or on the Discord server. I'm available both of the places.
Perfect. Okay.
Okay.
Thank you so much, Varun. Folks,
okay.
See you next time. Have a great weekend.
Okay. Bye-bye, everyone.
Goodbye.